we are very happy to welcome Carlo Carminati from the University of Pisa for our second talk today. And the title is Global and Local Minima of Generalized α-Brjuno Functions.
Okay. First of all, let me thank Irina and Felix for the kind invitation. I'm very happy to present this work here. This work was done while Irina was in Pisa, so it's is a joint paper with Irina and Stefano Marmi, and it's already on the archive, and it has already been submitted, and hopefully it will appear on Monad's head. Let me first define the object we work with. First notation about continued fraction. This is the classical Gauss map that everybody has seen, and which is at the basis of the continued fraction expansions, in the sense that, everyone knows that every rational number admits an infinite expansion, continued fraction expansion, something can be written in a form like this, and this converges. And usually one records the partial quotient like this, just to save space. And one interesting thing, a relation between the Gauss map that is called A1 and the expansion, is that A1 acts as a shift on the continued fraction expansion of a number. So this is all you have to keep in mind. And so there are some useful formulas, which are the formulas which relate the partial convergence, which are the rational values you get if you truncate the expansion at a certain point. And so you can write the initial point as a fractional transformation applied to the nth iterate of the Gauss map, and you can do also vice versa, because fractional transformation are easy to invert. And you can define these quantities, which are the products of the first n+1 elements of the orbit of Gauss map, and you can consider this function, which is called Bruno function. Actually, this version is Jacob's Bruno function. And this is what this function looks like. We will discuss a little bit, the whole talk will be about this function, property of this function, and related function which are related to this. But before going further, I have to, I should have apologized at the beginning, because today you will see very little dynamics. But this function comes from dynamics. So my apology is about, and actually this function more or less came out in different forms. This is the form Jacobs used. This is another equivalent form, and this is another equivalent form, and this is why basically you can get from one to the other. So you see, beta n-1 is more or less 1 over qn, this factor here you have here, and 1 over xn, has an integer part and has this part. This part is between 0 and 1, so it's not very big. So what can be big is this. So you see, you have here the log an+1, which replaces this, and the same is here. You easily see that all these three functions differ by an infinity function. So this is why okay, at the beginning, this is the origin. I think this is the one that Bruno used originally. At least I was told so because I think the paper is in Russian, and my Russian is not, well, is a zero, basically. Bruno, back in 1973, proved that if a number theta has Bruno if the Bruno function of that number theta is finite, then the holomorphic germ, which has linear part e to the 2 pi I theta, is linearizable. Okay. Next slide, we will see. I will say what linearizable means in the particular case of the quadratic map. So in this slide, so linearizable means that you can have a holomorphic map which is normalized with the 1 plus higher order term, which turns your dynamics into a rotation. And okay, here it's written for p theta, but it is the same for any holomorphic germ. And what your codes prove is that if you call R theta the radius of convergence of A theta, then the polynomial p theta, that quadratic polynomial, is linearizable if theta has some good property, namely if the Bruno function on theta is smaller than plus infinity. And in fact, your codes show that this difference, so the difference between d1 of theta and the logarithm of the inverse of the radius of convergence is bound.
Bounded, I think your construct is bounded from one side, right? But, I think your construct that it is bounded from one side, from above.
Okay. I thought, well, okay, maybe I'm not I'm not so much precise, but because afterward the final yes, maybe okay. The if I'm on the if I'm sure, on the other side I'm not sure, but certainly Buff and Sherita proved that this y is continuous, and the conjecture, which is due to Marmin-Musayo codes, is that y is 1/2 further. I write this not because I'm going in that direction, but because this 1/2, this further exponent will come back again, and in some sense might be linked to some renormalization procedure or something like that. So this is actually there is some later work which goes in this direction, which Sherita, Shiragi, I don't remember if it was also Buff, but I will not definitely pursue that direction.
Is this first condition we wanted finite? Is this like easy to work with it? Is it a good
well, what
to verify that the first one? Let's say I want for some theta verify that the Bruno function is finite at that theta.
Yes.
Is that usually easy? I mean, I'm trying to understand if this
okay. You have basically you have to work hard to build something that is not rational, but for which the Bruno function is infinite. For instance, Diophantine thetas have a finite Bruno function. So a large amount of this function is finite for many numbers. And I don't know if this is the answer to your question. Okay.
But to comment for a dense G delta set, it is infinite.
Okay.
Yeah. Yes, you can. You just if you want to play, you can the most handy expression to play with is this. So if you are just interested is finite or is infinite, you use this expression and you play symbolically, and you can build something exactly where it's infinite, exactly where it's finite, just tuning the AN. Okay, so this is
But the theorem you also formulated, the difference of these two functions.
yes, the difference.
And what can you say about each of them?
We will try to say something about this B1.
This is different.
I just wanted to say that it's a function which has some history, has some links with the dynamics, even if in this talk we will see basically no dynamics.
Okay, again, then you switch to B1.
Yes, and now we will switch to B1. And actually, one reason why I said this is that the kind of theorems that we give for B1 might be tried, might be pursued also for this function, for instance. Well, one could try. Okay, I can I can prove something about the global minima of B1. Could I transport it here as well? Of course, transporting it here is much harder because for B1 you have a functional equation which is neat and easy. For also this, if you work with this, you have a renormalization procedure which comes with the estimates, and it's much more. It's much harder to have a result for theta. But in principle, you could hope to transport the result from here to here. At least it's plausible. It's not. So this is okay. Properties of B1. Of course, B1 is periodic because by definition you take everything. Well, by definition, you ignore what happens for the A0. It's defined only from A1 onwards. It's an L1 function and blows up at rational points. Blows up at rational points means that the function is over some logarithmic function with the singularity at rationals, and of course. At 1/2, the logarithmic singularity is harder. The smaller the denominator gets, the weaker the singularity. Okay, so there are singularities all over the space, but just you cannot see them, or if you prefer, my computer, my program did not run long enough to show them. And okay, you have this functional equation, which is quite easy to work out, and you also have an analog, a k iterate of the functional equation, namely you can write B1 as the first term plus a rest, which is written like this, or a sum of k plus 1 terms plus a rest, which is written like this. And B1 is lower semi-continuous. So by general you know that B1 will admit a minimum on 0, 1. Lower semi-continuous function on compact space has a minimum. And the problem is, where is this minimum? Because to locate it, you don't have you don't have a differential calculus, of course. But the function is not even continuous, so it's quite tricky. And okay, before going on, I want to show a first result, namely, which you could easily imagine if you if you consider the graph of this function and you close the graph, so you close the graph in R2, you get the part above the graph. So here it's small game, and you draw 10,000 points. The function with 10,000 points, and then 100,000, 1 million, 10 million. Of course, this is a silly game, and nobody would do this seriously, but just to show that with some patience you fill up everything. Of course, it will be very hard to fill up even up to 7 with the computer, nowadays computer, but this is the general result. So everything gets filled.
Excuse me, so here alpha is any or alpha equal to?
Oh, sorry. Okay. Think about alpha is okay. If you know what v alpha is for any alpha, it's true for any. But here I should have written alpha equal to 1. Sorry. In a short, okay, the picture are for alpha equal to 1, and before the end of the lecture, I hope I will talk to you also about general alpha. So, what about minima, or better to say local minima? Well, okay, by lower semi-continuity, a minimum exists. And a nice theorem by Balazard and Martin shows that the minimum is taken at the point G, which is the golden mean. And it's a nice trick. They use the fact they know a priori that the minimum exists, and they show that it cannot be smaller than G, it cannot be bigger than G, and so it must be G. It's quite.
Also 40 years after it was introduced, right?
Yes, so nobody, maybe nobody was so interested in this problem. But I think that this result, I very much like this result because it's nice.
Might be intuitive that this clear, but there's the lowest possible approximation.
Yes,
well,
it's yes,
but
intuitively, okay. Often here intuition is sometimes is not often, but sometimes is misleading. And what about local minima? So, for instance, what is the minimum between 1 and 1/2? Between 0 and 1/2. This is you could pick up any interval and you could ask what the minimum is on this interval. So I don't know whether this is interesting, but it's a nice problem. And for instance, we proved that the minimum between 0 and 1/2 is what Felix thinks. Which is 1 minus G, which is the one that has the lowest partial quotient here, and then all ones. And then you could ask, okay, what about all, let me first define a noble. I call a noble number a number which ends like the golden mean, which has the same tail as the golden mean. And the idea of proof in this case to prove that G squared is actually the minimum is very simple, because you use the functional equation at the different stages, at different, and you get, with the first approximation, you show that the minimum cannot be on the left of G squared. G squared is the same as 1 minus G. Sorry for being sloppy. So you show first with the first approximation, with the first version this functional equation that the minimum cannot stay here, and then you show that it cannot be bigger than 2/5, and so you cover the range between 2/5 and 1/2, and then you use yet another approximation, and you show that it cannot be even between 0 and between g squared and 2/5. So it's really an easy, an elementary proof, but which it's difficult to be replicated elsewhere. So the characterization of local minima, if you call n the local minima of B1 and noble numbers, at this stage you would assume, you would guess that n is equal to n. And this is what we try to prove. And unfortunately, we did not succeed completely. But, okay, this is an alternative formulation, which is even more precise. This formulation implies this.
Excuse me, which intervals are you now considering when you're talking about local minima?
Pardon?
Which intervals?
There existed.
Any subinterval?
So
No, because I thought maybe you are choosing a rational endpoint, but no.
No, it's not. Local minimum is just a point where the function is smaller than all nearby points.
Ah, okay.
Okay, so the statement which I believe is true is this. So if you consider the cylinder defined by a1 and an, so you consider the function which have this first question and then anything, the minimum of the cylinder will be the one, simplest noble number in that cylinder. Okay, so.
So this equivalent, you know, that is
Well, it's easy to show that this implies this. They are not equivalent. This is stronger, but at least it's a more precise statement. So, if I would try to prove this, I tried to prove this. I did not succeed, but okay. So the theorem we have is that if psi is a noble number, then it's a local minimum. So we can prove that all noble numbers are local minimum. And a key ingredient to go in this direction is that G is a cast-like minimum. So even if you don't notice from the picture I showed you before, the B1x minus B1g, this is known to be positive by the Balazard result, is bigger than x minus g to the power 1/2. So this power 1/2 comes out again in this. And for instance, this is a log-log graph. So on the x-axis you find log of modulus x minus g. And I use the two colors depending whether x is on the right or on the left of g, so you can distinguish the. So it's like if you folded two graphs together. And on the y, it's the difference between the logarithm of the Bruno functions, and sorry, it's the logarithm of the difference, of the values, and you see that there is a linear dependence. You can.
So how can you recover the inequality from the graph? What do you need to do?
Pardon?
How can you recover the inequality from the graph? I mean, what?
No, you don't recover the equality from the graph. I'm just trying to visualize what's going on,
But how do you visualize? I mean, so do you need to think that there is a slope 1/2? Yes.
Sorry. Yes. probably if you examine the scale, you see that this is a slope 1/2. But you can prove it directly, so it's not so much. So why this theorem implies theorem 8 first? Basically, the strategy is to show that a cusp-like minimum, so if G is a cusp-like minimum, then any image of G in this way is again a cusp-like minimum. So, and basically you transport the geometry of being a cusp-like minimum from G to all other pre-images of G under the Gauss map. So this is, it's easy, it's the easy part. So the hard part is this inequality, and I try to explain how you work. This phi of x is a map 1/1 plus x that in the symbolic picture is just amounts to adding a 1 at the beginning of the expansion of the number. So if you start from psi 0, which is 0 1/2, and you write psi n, which is something obtained iterating n times this transformation. Observe that this transformation is order reversing. So you must be careful because it always reverses the order. But the union of the images of 0 1/2 is basically the whole interval apart the point, the value G, and this is almost a disjoint union. So you get adjacent intervals. So basically, what you get is here you have 0 1/2, 0 1/2. Here are the values which do not start with 1, and this is mapped here, which are the values which start with exactly 1, and then the next digit will be different from 1, and then you get here something else, which are, so this is no 1, this is 1 and something else but different than 1, this is 1 1 something else which is different than 1, and this, in this way you tile the whole interval 0 1. What is missing will be the point G, but what happens in G you already know. And this is almost disjoint union, and you write this delta n and epsilon n, these differences. And okay, and what you can prove is that there exists two constants which do not depend on the initial condition, such that you get these inequalities. The first inequality is more or less obvious. It comes from an easy estimate in continued fraction. We play with Fibonacci numbers. The other is much less trivial. And so the game is that you play this game, you get an estimate here, and from this estimate you get an estimate here, then an estimate here, an estimate here on the whole. And what you want to see is that this converges to this gives you a shape, like a cusp-like shape, so essentially. And you see that here you have 2n, here you have 4n, and this the fact that this is exactly the square of this gives out the.
What is xn in the definition of epsilon?
Sorry.
Xn.
Oh, sorry. It's xn.
Okay.
Xn. Sorry. In principle, I wrote xn, but I realized that xn was another thing, and so I changed. Sorry, xn. And but I did not change ever. And okay, and this. Okay, there is a typo. There is another typo here. It should be epsilon 2n plus 1. So 2n plus 1 bigger or equal sigma g to the power 2n. We need to have the same index here and here. And what was okay? Okay. So this will show the inequality just on one side, just on this side of G. But to get it on the other side, you just use the functional equation. So it's not. This is the hard step. Now I see that. Let me see if. No. Okay. I wanted to give you what maybe it's not. I realized that I have downloaded not the very last version of the file, so there is a part missing. So let us go on. Okay. Sorry, I will not give you the proof, or not even an idea of proof. Basically, what one does is writing this difference. Writing this difference gives you an inequality which is of this kind. It's easy to get. Okay, I will use the blackboard to give you a very quick. What is the very quick idea of how the proof goes and why we get it only on one side. So playing with the numbers, you get something like epsilon n plus 1 is bigger or equal. You get an equality like this: psi n plus 1 epsilon n minus some L which is positive delta n plus 1. So this L is 1 over G minus V1 of G, which is bigger than 0. So playing with the functional equation, you can get this inequality. This inequality, okay, such inequality would be very nice if you did not have this term, because you would have that this psi n plus 1, of course psi n goes to G, and also psi n plus 1, so you would have that this is bounded below by something that goes to 0 in a controlled way. Unfortunately, there is this term, which is a nuisance. And what we did is to take to iterate it twice. So, and write epsilon n plus 2 is bigger or equal than, okay, you have psi n plus 2 epsilon n plus 1 minus L delta n plus 1, sorry, epsilon n plus 2 L delta n plus 2 here. I just rewrote this at the next level, and then I substitute this. So you have epsilon n plus 2 bigger or equal what? Psi n plus 2 times this whole thing, psi n plus 1 epsilon n minus L psi n plus 2 delta n plus 1 minus L delta n plus 2. So here you take out the L, the minus L, so I write it like this. And now we are almost done, because what you want to see is that you can say something about this, the sign of this term. You would like this term to be positive. Actually, it's not always positive, but the sign of this term depends on the party of n. Because if you write who is this guy is psi n plus 2 times delta n plus 1. Delta n plus 1, you write what it is, psi n plus 1 minus g plus psi n plus, delta n plus 1 and plus 2 minus g. So this guy, which is in the braces, is this, and now you just divide things. So this is psi n plus 2 times psi n plus 1 times, let's say minus g over times psi n plus 2 plus 1. But this is 1 over psi n plus 2 by definition. So this is 1, the first term is 1, and this is 1 over psi n plus 3. And so this term is bigger or smaller than 1 depending on the parity of n. And this leads to the inequality. So this is the only clever thing of the whole lemma. The rest is inequalities, playing with the classic inequalities using convex inequalities for the logarithm and so on. This is just the base of the trick is this. So you get so this is 1 in the end, this is 1 minus g over psi n plus 3. This is the bottom line. Okay, so I don't pretend I gave you a proof, but I hope I gave you an idea how to get through this proof. So what else? So we were happy with this. We were sad we did not, we couldn't attack we could solve the conjecture because and we said, okay, let's try to better understand what's going on, how it comes that G comes out. And so the idea was to go towards some different alpha continued fraction algorithms and see what happened in that case. So there are other continued fractions, probably if one does not work with them, hasn't ever seen, but one which is famous is Hurwitz's nearest integer continued fraction, where instead of taking the integer part, you take the nearest integer approximation, corresponds to that, and the Gauss-like map which corresponds to Hurwitz's continued fraction is this. It's very nice because it has complete ranges, so it's even from the ergodic theory viewpoint is a nice map. And actually there is a whole family, continuous traction which connects, which goes in a continuous way, I would say, from Gauss map to Hurwitz and to the backward continuous traction. Morally, it goes like this. You draw, okay, when you draw Gauss map, you draw, okay, the branch 1 over, okay, this is 1 over x, and you take the integer translate of 1 over x vertical. So you have 1 over x minus 1, 1 over x minus 2, you have all these branches. And if you want to have something on the other side, you take 1 over modulus of x on this other side. So let me do the picture, and you have all these branches which are symmetric. I draw them on this side. So if you look into what happens in this window, you see the graph of a Gauss map. But you could take this window and slide this window, keeping this square, keeping the edge equal to 1, and see what you see here inside this orange picture, okay. And since the size of the side is always equal to 1, what you see inside in this window is still a map, because this branch ends where the next starts. If I did, and actually, what people often do is folding this picture. Since this part is symmetric, when you fold this part, the branches here go on the branches here, and then you fold also the other part in this way, and you get the so-called folded A alpha. So basically, you can the interval on which the map the new Gauss-like map will be defined will be 0 alpha or 0 alpha bar, where alpha bar is the largest between alpha and alpha minus 1. You see, this is alpha minus 1. When you fold, if alpha is bigger than 1/2, this part gets in, but if alpha is small, when you fold, this part is dominant on the other side, so you get this alpha value. And I alpha is defined like this. It's similar to Gauss map for x different than 0. And this is the kind of graph you get. And you see here there is this nuisance, which is a nuisance for every problem, which is the incomplete branches. They are of the same size because they come from backfolding. Almost all, because this has a different height, but they are incomplete, and this makes things possibly more complicated. So the α-Brjuno function is defined in the same way. First, you get x, you get x0, which is representative in your interval. Like before, we got x in 0, 1. Now we get x in this x should be in I alpha, and then you apply this Gauss-like map and you play the same game. So this x0 will be called the canonical representative. By construction, this new Gauss-Brjuno function. Okay, you have so xn is simply the n iterate. And the beta are defined in the same way. They are all positive, these guys, and okay, you could all see, write all the formulas, and the α-Brjuno function is defined like this. In the formally, it's just in the same way, but it's a different function, of course. So the properties of the alpha is one periodic and positive. It is at one, it blows at rational points, you still have the functional equation, and B1 is lower semi-continuous if alpha is rational. Okay, one. Pardon? B alpha, sorry. Here, sorry, this is B alpha. Of course. One could say, okay, we can prove that B1 is lower semi-continuous if alpha is rational. Maybe it's shortcoming of our proof. No, it's not. It's not just a technical issue. And you can cook up an example where actually the function here is defined as this, and the limit is down here. So you can show that it's not always lower semi-continuous, but something even worse happens, namely, okay, this is just numeric, but if you take alpha equal g, so the golden mean, you have that it looks like that the minimum does not exist for this particular value. So, okay, this is numeric, but the numerics is quite strong, because okay, this phi is what before I called this should be phi square with the notation before, means putting two ones in the front of the expansion of x. So if you compare the value you have in x for x in this range, and the value you have when you put two ones, okay, this is always positive. So adding ones gets the function, decreases the function, and it seems that the limit is this value, which it seems that the limit is this value, which I don't know what it is. But the function at this point, at the point g, has a very precise value, which is above here. So there is a very strong numerical evidence that for BG does not for BG the minimum is not attained. It's just a minimum. So for BG, for instance, we couldn't possibly play the same game as Balazard 10 because
so if you avoid carefully, can you actually prove it using the computer system? That
well, I did not try. We had to close the paper. We had the deadline. Actually, we did this after we got the first revision. The referee asked, "Why did not you investigate more what happens when alpha moves?" And we did it, but we had the deadline to resubmit the paper. And so I think it's doable, but we couldn't do it in 1 month. Also because we had the other revision. Anyway, you can say, okay, I can play with some numerical evidence. Okay, I know that in general the minimum does not exist, but computers use rational numbers, so computer naturally chooses the right parameter. And I can see, I can shoot 1 million of points between 0 and 1 and see where the minimum is. And you get this graph. On this graph you have alpha on the axis, and either the point of minimum or the value of minimum of the alpha numerically. And so this is an estimation. And what it seems is that the behavior is this. The shaded part corresponds to the parameters where we can actually prove a result. So you see that You can prove the result between G and 1, you can prove the result between gamma, that is square root of 2 minus 1, and some other value which I will tell you who it is. But even on the left of G, there is something which is not very, which we do not understand, and we believe here there is a jump. And here also there is a jump. Okay, it's intriguing. Of course, if one likes to play with alpha fraction, it's nice. What strikes is that it looks like a almost everywhere constant function, and actually here and here it's constant. But I believe that this is true in general. And these values, which are at the point of minimum, where the minimum is located, are all algebraic numbers, so more quadratic irrational, at least conjecturally. So the first result one can prove is follows from Louis' lemma, because one can prove that the alpha, when alpha is between G and 1, so in the rightmost shaded region, the alpha of x is bigger than b1 of x, but the alpha of G is equal to b1 of G. So if G was the minimum for b1, it will be the minimum also for the alpha by obvious, and you don't even need alpha to be rational. Just you have it for free. You have the result for free, and also you get the cusp-like structure for because you had before, because it remains. So this is the easy case, and this okay. I tell. This is linked with a property, which is a property of alpha continuous fraction, which is called matching. And I will not discuss, I will give you an idea of what happens later on in a moment. So, and what else? Another case where one could try to say something, and which is interesting, is alpha equal to 1/2. This 1/2 case cannot be deduced in a straightforward way from alpha equal to G, and in fact the minimum changes, something changes. And but in this case, since you have complete branches, you can repeat the Balazard-Martin argument for alpha equal 1/2, and changing what has to be changed, you can conclude that the minimum is b1/2 gamma, where gamma is square root of 2 minus 2, 1. And also the scaling argument can be repeated, and you get that all A1 inverse integers of gamma are local minimum of b1/2, but of course you don't have the complete characterization. Okay, no, this is okay, this is okay. What you can prove, you can compare now. Okay, we want to go beyond 1/2, and we can show that if you pick up alpha and alpha prime, forget this first line. The idea is if you pick alpha and alpha prime, which are either on the right of G or sorry of gamma. Of 1/2, either between 1/2 and G, or are between gamma and 1/2, and if they are on the right, they should not be too far from one from the other. Okay, and if you pick these values, and okay, you go and compare the two orbits, or the orbit, you pick up x and you pick up the canonical representative in your interval, and you compare the orbit, you get iterating A alpha and A alpha prime. And, okay, sorry. Then you can write the difference between the Bruno function, and this difference is a sum where basically, okay, this is a faulty slide because how much time do I have? 3 minutes. Okay. Okay, you get that the sum is the sum of the beta k minus 1 times some function, hi of xk. This function is different, is something like this. This function which is there, hi of xk, is something like h of xk times chi I of xk, where chi I is the indicatrix of the interval, I would say alpha prime alpha. This is I. So it's a sum where you get something only when xk, which is the iterate of x alpha k of x0, is in some small interval. And okay, here you have also an explicit form for the function h, but you would not. Okay, here it's a picture. In this picture, you have alpha prime, which is 0,5, alpha is 0,56, and the interval alpha prime alpha, so this interval I was mentioning, is this. And here you see in yellow, you hardly see it because it's colored. It's the function h, which should be considered just on this interval. And basically, you have that for the difference is given by sums of h, but for the sum ranges on the k's for which xk goes in this interval. So you have the main curve, which follows the yellow curve, which is sort of the contribution of the first passage through this interval. And then you have these airs, which are contribution of second and higher order passages through this same interval. So it's it comes out some dynamics here. And this explains the reason of this fractal picture. And the fact is that as far as this function h is positive, you have that the graph moves in one direction. So when you change alpha, the graph moves upwards or downwards, and but in the same direction, because you always and you can show that you have basically b alpha of gamma stays the same, because gamma is a fixed point for every b alpha in this range, but the function gets up, and you have the same situation as in the case between g and 1. And okay, and how much can you push this argument? You can push this argument as far as h stays positive, which unfortunately is not up to g. And this is why you get a partial result. And, okay, this is more or less everything. Sorry if I was late.
Thank you very much. Are there any questions? Yes.
I have a question. So concerning the original Bruno function, can you show that for some numbers x that they are not local minima. For instance, if you take x other periodic points like 2, 2, 2, 2, 2.
Okay. I did not try anything with the original Bruno function, but actually I once worked with the second function. So let me. The original Bruno function is some log qk plus 1 over q.
No, I mean, sorry, by original I meant b1. So
Okay, b1. Sorry,
denoted by b1.
Okay, b1. What about b1?
So you show that all noble numbers are local minima.
Yes.
But for some other numbers, can you show that they are not local minima, for instance?
Yeah. Okay. For between 1/2 and 1, I can show that the global minimum in that is in g squared, which is 1 minus g. Okay. If you pick one other, okay. In principle, I think that if you pick up a noble number, you can prove by hands that that noble number, that the second conjecture I wrote. So if you pick x equal 0, a1, a2, a3, an, and then ones, I'm convinced that you can prove that this is the minimum on 0, a1, an, and then whatever. So if you give me some a1 and you ask, prove that this is a minimum. Okay, I go there, maybe I stay one day and I prove. And then you give me another one. Okay, maybe I can prove this other one as well. But of course, there are many. So we do not have something that works in general. So I don't see how to make this work in general. So I did not push very much in that direction because, of course.
I don't understand how this answers your question.
Yes, I think I answered with the opposite question. So, can some number x, for instance, which is equal to 2 in period, can you prove that it is not local minimum?
2 in period is not. I can prove that 2 in period is not a local minimum because you have 2, 1, 1, which beats it. It's in the same cylinder.
But you can choose smaller interval on which it will be.
Okay, I understand. No, yes, good. Okay, I understand.
Those cylinders cover the whole interval 0, 1. So if you claim that take some other point and some cylinder which is the minimal point, in this interval, you can find a cylinder which contains your original point, and then you have a contradiction, because in the cylinder, some other point is in the
Isn't that meant for the conjecture?
No, if you do this, then this is conjecture.
So this is not known.
No, it's the thing.
Conjecture.
Okay.
But I think Alan asked about the
Specific point.
Let's show the conjecture. Let's show that the specific point is not local minimum.
Okay, good question. I did not think about this because I was trying to get the global result, but it may I did not try, and maybe thinking about it for a specific number would be instructive. I agree. Now I understand the question.
Thank you very much again.
I have downloaded the wrong file.
What about recording? So it wasn't recorded.
Pardon?
Seems that it wasn't recorded.